So finishing up 3.3 here, example 8. For both of the functions below, determine the intervals of increasing, decreasing, and the x-coordinates. Notice just the x-coordinates of the local extrema. And then, of course, I was going to justify. So this will be a little anticlimactic after the warm-up. So this will just be kind of like reinforcing it. The note up above there says be careful of discontinuities, that is where the function is not defined, like vertical asymptotes. Because they are not going to be critical values if they're not in the domain, but they are very important values, and they will find their way into the chart simply because, as we saw previously, a graph can change its increasing, decreasing behavior at a vertical asymptote. But we wouldn't call that x value a critical value, and we certainly wouldn't say that it's a local maximum at that x value, right? So we got to be careful about those. For continuous functions, we just put local extrema or critical values in there. So step 1, what's the domain of f? Think about that first. Any restrictions on the domain? X can't be 0. Okay, so we already know that. Has 0 already made its way into the chart? Yes. Whether it's a hole or whether it's a vertical asymptote, we don't care at this point. It's made its way into the chart. What is it, by the way, a hole or a vertical asymptote? It's a hole. Because when you plug in a 0 for x, what do you get? 0 over 0. So remember, that's a hole. All right, so if you want to kind of think about it as like playing the EVT game, there's x equals 0. He is in the green room, and it's a very small room. He barely fits in there. Hope he's not claustrophobic, because we have some more things to find. I wonder if I can shrink it down even more, make him nervous. Oh, not like that. Oh, I am recording this. I'm thinking of that Star Wars, you know, where they fall into the trash compactor. Okay, we'll stop right there. We are recording. We need to find critical values. How do you want to take the root of this? You want to Hody high, or do you want to split it up and use the power rule? Both methods work. Splitting it up. I would go Hody high because if I split it up into the power rule, then I'm going to have two terms, and I'd rather have it as a single termed fraction if I'm going to have a fraction at all. And remember that the Hody high rule, quotient rule, preserves that. So here we go. Ho d high is 3x squared plus 1. Hody high minus high. D ho is 1. All over ho ho is ho squared. As I told you in the warm-up, you first want to look for anything that's common in your two terms because it's partially factored, believe it or not. The two terms are partially factored. Did I not? I did not mean to. That's me being just hasty and careless at the same time. Hasteless. No, that doesn't work. All right. Without, yeah. Thank you. Is there anything common that we could factor out? There is an x, right? There's a hidden x. There's a hidden x. So let's try that together. There's an x there, and there's a hidden x in these two terms, right? So let's go ahead and do that. You could just expand it all out. In this case, it wouldn't be too bad to completely expand it all out because it's not going to be that ugly or cumbersome. But it's just a method of efficiency. Look for common factors. So I pull that out, and I'm left with 3x squared plus 1. If I factor an x out of x squared plus 3, I'm left with minus the quantity x squared plus 1. Correct? And you can even maybe do two things in one there. You can distribute the negative like I unintentionally did and say that it's x squared minus 1 if you're comfortable doing that. So we already know one of our critical values, don't we? What value makes the numerator 0? 0. So is 0 a critical value? He makes the derivative 0 in the numerator. Hey, 0 is already getting compacted over there waiting, remember? He's trying to show up again. 0 is, he's trying to show up as a critical value. He really, really wants so badly to be a critical value. He makes the numerator 0. That's funny. All right, so if we clean up what's left, we get 3x squared minus x squared. That's 2x squared. And 1 minus 1, really? It goes away? Wow. What happens here? X squareds divide out, you're left with 2x. So, if I set that equal to 0, I get x equals 0. Is it a critical value? No, not a critical value. He also made the denominator 0 of the derivative. He's trying to be a critical value, but he's not. He wants so badly to be a critical value. Do we have any critical values? No. Is there anything to test then for intervals of increasing, decreasing? Yeah. We still have a vertical asymptote. So here we go. X and F prime. 0. Why the dotted line and the dashed line? I don't know. But draw it as a dotted or a dashed line. Because you want to remember that it's a what? Vertical asymptote. Yeah. -1, 1. Plug them into the derivative. Negative. Positive. Ooh, local min? Yeah? Local min, anyone? Local min? Anyone take the bait? Local min? No. Why not a local min? It doesn't exist there. So, yeah, if you remember to put your vertical asymptote in there, but then you draw it as a vertical line, you may forget that it's a vertical asymptote. So, we could say this, F is decreasing on the interval from -infinity to 0 and increasing on the interval from 0 to infinity. Now it says to determine the x-coordinates of any local extrema. Are we going to have any local extrema? I don't think so. The function is not defined at 0, right? It's decreasing everywhere to the left of 0 and increasing everywhere to the right of 0. The only place where there would be a local extrema would be at 0. It would be a local min if it were defined there. Is it defined there? No, it's not. So we'd have no local extrema. Simply because it's decreasing everywhere to the left and increasing everywhere to the right. Now what if I made this a piecewise function? Bless you. And I said, let it be f of x when x isn't 0. Otherwise, let it be 2. Would it change our analysis for the derivative or the increasing, decreasing? No, because it's still the same function everywhere to the left of 0 and the same to the right of 0. But what's going on at 0? Is it a local max or a local min? There's a what there, did we cite earlier? There's a hole. So it depends where the y value of the hole is, right? The limit, essentially, as x goes to 0. If that y value that I just gave you is above the hole, then it would be a local max. If the y value that I gave you is below the hole, it would be a local min, right? How can I figure out what the y value of the hole is? Yeah, let's find the limit as x goes to 0 of f of x. Well, we know how to do that. That's the first method we learned, right? Factor out an x. And what happens with the x's? Oops. Yep, collateral damage. Be careful, guys. Plug in your 0 for x and you get 1. So that function would have a hole at 0, 1. So if I defined it to be 2, it would be a local max. Now that's kind of weird. You would have a local maximum at x equals 0, even though the slopes change from negative to positive. I thought it changed from negative to positive slopes was a local min. How can it be a local max? Louder? Ah, very good. We can't do the first derivative test is what you're saying because this function is not what at 0. It's not continuous. So instead we just say immediately, there goes Emilio again, immediately to the left and immediately to the right we have y values that are lower. Perfect. So the first derivative test only works for continuous functions. Cool. From the beginning, absolutely. Yes. Yes, and then the derivative of x squared plus 1 is 2x. Very good. Absolutely. Simplify when? Early and often. Huh. And that's exactly how I would do it if I were doing this problem. As long as once you do that, though, you got to keep in mind there's a hole there, and then it works perfectly. Yeah, that was going to be my follow-up question. How can we do this a little bit more efficiently? Factor it out. Know it's aligned with the hole. Okay, very good. And then you can look at it right away and just say, well, it's actually the derivative. Sorry, is going to be a parabola. The function is going to be a parabola with a hole, and the derivative is going to be a line. Okay, let's look at this one. Domain. Any domain issues? X can't be 0. Now, unless it asks you specifically for the domain, you don't have to pretty it up and make it like all formal with the braces and everything. Just know the X can't be 0. Is it a VA or a hole there? It's kind of important to know. This one's a VA. It's non-removable. You plug in a 0 for X and you get 1 over 0. Actually, negative 1 over 0, which is still some type of infinity. So we know there's a what there? VA. Is 0 going to be a critical value by definition? No. Will it be an important value? Yes. Welcome to the chart, X equals 0. We'll give you a little more room this time. For now. Oh, man, messed it up. I don't want to mess with 0 again. He's already tormented enough. All right, so how do you want to treat that negative? Do you want to split it up? Last time we did the Hody high rule. You want to try the old splitting it up method this time? Let's try it. The old splitting it up method. I will leave the negative outside. When you split it up, x to the 4th over x squared is x squared plus 1 over x squared. There you go. What would you do with the negative? Would you keep it out front or would you distribute it? Keep it out front? Yeah, me too. Notice x still can't be 0 in that second term. So I get x squared plus x to the negative second. And when I add those together, I get 0, right? Algebra 1 students, maybe. Yeah, okay, cool. Now we're ready for the derivative, f prime of x. The negative 1 out front now is a constant multiple. It goes along for the ride. Times the derivative of x squared is 2x. And this becomes minus 2x to the negative third. Now if I clean that up, I get negative, parenthesis, 2x minus 2 over x cubed. I still would recommend highly getting if you have at least one term that's a fraction, make it all into one single fraction. It's going to be a lot easier. So now we need a common denominator. Or you could have factored out least powers. What's the common denominator? X cubed. So if you multiply this first term inside by x cubed over x cubed, you get 2x to the 4th minus 2 all over x cubed. And we're almost ready to go. I'm going to say that's f prime of x equals, I'm going to factor out a 2 and call it negative 2 times x to the 4th minus 1 all over x cubed. Now we could still factor the top a little bit more. I kept the negative that was already here, and I just factored out a positive 2. You could, and then it would be 1 minus x to the 4th, and that negative out front would be gone. Do you want to do that? It doesn't matter to me either, as long as it's correct. X to the 4th minus 1 is the difference of squares. You'll see that? It factors into x squared minus 1, which is also a difference of squares. That factors into x plus 1, x minus 1, times x squared plus 1. How far do you want to factor it? What's the purpose of factoring it? Twofold. To get your x values that cause 0 easier. We know which ones cause 0 already, don't we? What are they in the top? Plus or minus 1. So factoring it as x minus 1, x plus 1 times x squared plus 1 is not going to help us. We also want to factor it so that we can look for the signs of our products and quotients a lot easier. I think it's easier just to plug it into x to the 4th, don't you think? So at this point, I would probably choose not to factor it all the way. So f prime equals 0 when the numerator equals 0, which is x equals negative 1 and positive 1, and f prime equals d and e when x equals 0. How many critical values do we have? 2. Good. I can't trick y'all. Not anymore. Not anymore. 0, welcome. You showed up here, but you're not in the domain of the function. You've already made it to the chart, 0, so Don't feel bad when we're excluding you from the critical value club. But these are in the domain. So we got x and f prime. Negative 1, 1, and at 0, of course, we're doing what? Vertical asymptote. I don't know. It's just my finger sticks. It's the glass. It's the glass. It sticks. It's also me being consistently inconsistent. Let's pick some numbers. Negative 2, positive 2, and then I'm stuck. Help me. Negative 1/2. Yeah, 1/2. That's what I would have chosen. Nice. And we're plugging them back into here. Now here's where Mr. Rapp said if you factored out a negative from the inside and call that 1 minus x to the 4th, then the negative 2 becomes positive 2. You wouldn't even have to worry about it. But because I kept the negative 2 out there, I just need to realize that that negative in front of the 2 is going to change the sign in the numerator from whatever x to the 4th minus 1 gives me. And the bottom, do I need to worry about the bottom, or is it always positive? I do need to worry about it. Maybe not worry about it, but at least concern myself with it. If you cube a positive number, it stays positive. If you cube a negative number, it stays negative, right? So just realize that the denominator preserves the sign of the number that you're plugging in. We don't really care about the values. So here we go. Plug in a negative 2 into the top, and we get negative 2 to the 4th, which is positive big. Minus 1 is still positive times the negative 2. So I have a negative in the top and a what in the bottom? Negative. And a negative over a negative is a positive. Whew. All right, plug it into negative 1/2. Cuidado, careful. Negative 1/2 to the 4th is positive 1/16. And 1/16 minus 1 is negative. And a negative times a negative is a positive. So we get a positive in the top, a negative in the bottom. Positive over negative is negative. So you got to keep track of signs, but you don't have to keep track of values. That's pretty nice. And if you plug in a positive 1/2, you're going to get the same thing in the top, right? Because the top is an even function. So you're going to get a negative times a negative, which is a positive, over a positive, that's a positive. Plug in a 2, you get a negative over a positive, which is a negative. There you go. So now you're staring at your intervals of increasing, decreasing, and you can also get your local max min. Here we go. Positive to negative, negative to positive. How am I doing? Not great. The whole purpose of having the dotted line there is so we don't put the smiley face there. It's a vertical asymptote. So we only have 2 extrema, and they're both the same type. So we can justify them in one sentence, can't we? Now, this is very similar to an AP question that appeared years ago. Students that didn't consider the vertical asymptote. Let's say you just went negative 1 to 1 in your number line chart. You didn't have the 0 there. When you're picking a number between negative 1 and 1, you might choose 0, right? It's right in the middle. And you would plug in a 0 and be like, oh, I didn't get an answer. That's kind of weird. Okay, well, I'll choose another one. And you choose negative 1/2. Now you're going to have a local max at negative 1, but what's going to happen? You're going to have a negative to the left of 1 and a negative to the right of 1, and you're going to what? You're going to miss this one. Or maybe you choose a positive 1/2, and you get a positive number, and now you're like, oh, it's positive on both sides of negative 1, so I'm going to miss this one, but you're going to get that one. That's like where you get a double penalty. You get a penalty for not considering 0 flat out, plus you're missing a whole big piece of the puzzle, so you're missing a local max, and you're going to lose points for that. So that's one of the times where your unintentional oversight of 0 will cause you basically 2 points out of 9 on a free response. So what goes in the chart? Critical values and discontinuities. Good. Let's go ahead and say the sentence. F has a local max? No, I don't think so. Has local maximums. How would you abbreviate max? Maxes? Like ES? I never learned that in my English class. Maxes? Max. That's hard to say an X and an S back to back. Max. What if it was plural possessive? Maxes. Yeah, Texases. How would you abbreviate? How would you pluralize Texas? There's only one, baby. You can't do it. How about local maximums? Circumventing the problem altogether. F has local maximums at x equals negative 1 and x equals 1, since F prime changes from positive to negative. at, I'm not going to write them again because it's going to seem silly. I know in the English language that's why we have pronouns. How about at each of these? That works. You do want to refer back to them somehow. You want to write them again, that's fine. You're not going to lose points for your lack of pronoun finesse. I would just, in general, say avoid pronouns at all costs. All right, that's it. Did it ask for the maximum values? I just want to check before I walk away. Are we looking for the x values or y values? Because there's a huge difference. Yeah, just find the x coordinates. Okay, good. Bless you. If you needed to find the y values, you would just take your -1 and 1 and plug them back into f, right? The original function. If you ever see a negative out front there, be very careful with it. It can mess things up, right? One of the things you could do is just to distribute it in the top and just now it's absorbed into the problem, or you could just take it into the bottom and keep it there. We chose to keep it out, and we had parentheses the whole time to guard against messing it up. All right. Oof. Lots of opportunities for careless mistakes. You know how to do the stuff, but little careless mistakes here and there. Details. All right. Any questions on 3.3 then? When's the worksheet due? Monday, yeah. Monday. Any questions from the worksheet? Okay, go ahead and download 3.4 then. And